Everyone is watching the race for more qubits, more power, bigger numbers. But while the world was distracted by that race, a lab in California solved a completely different problem, one that could matter more than any qubit count ever will. And it happened almost in silence. No press conference packed with cameras, no breathless keynote, no billionaire on stage promising a new era of computing. Just a quiet paper, published in one of the most respected scientific journals on Earth, describing something that sounds almost too simple to be revolutionary: a quantum chip that runs itself. To understand why that matters, you have to understand what quantum computing actually looks like behind the scenes, because it is nothing like what most people imagine. When you picture a quantum computer, you probably picture a sleek, glowing chandelier of gold tubing, hanging in a spotless lab, humming with mysterious power. That image is real. Companies love showing it off. But what that image conveniently leaves out is everything surrounding it. Because for every one of those elegant, glowing chandeliers, there's a small building's worth of equipment standing just outside the frame. Racks of electronics, miles of cabling, rooms full of amplifiers, signal generators, and processors, all working around the clock to talk to a tiny handful of qubits sitting at the center of that frozen chandelier. That is the dirty secret of quantum computing in 2026. The qubits themselves, the actual quantum bits doing the calculations, are almost the easy part now. Scientists have gotten remarkably good at building them. The real nightmare is everything else. It's the plumbing, it's the wiring. It's the sheer mind-numbing complexity of controlling those qubits from the outside world, using electronics that have to sit at room temperature while the qubits themselves sit colder than deep space. Think about what that actually requires. Every single qubit in a quantum processor needs a constant stream of precisely tuned electrical signals to function. Those signals have to be generated by conventional electronics, sitting outside the refrigerator that keeps the qubits cold. Then those signals have to travel down long cables through multiple stages of cooling into the heart of the cryostat, without picking up noise or interference along the way. And they have to do this thousands of times per second, with almost perfect precision, because quantum states are famously fragile. The tiniest disturbance can collapse them entirely. Now, imagine scaling that system up. Today's leading quantum computers have somewhere in the range of a few dozen to a few hundred working qubits. That's already a logistical headache, with enough wiring to make an engineer's head spin. But the machines that could actually change the world, the ones capable of breaking modern encryption, simulating new drugs at the molecular level, or modeling chemical reactions no classical computer could ever touch, those machines will need thousands or even millions of qubits working together. And under the current approach, that means millions of individual wires, each one carrying a signal from a warm room into a super cold chamber. It's not just impractical. At a certain point, it becomes physically impossible. There simply isn't enough room inside a refrigerator for that much wiring. And even if there were, the heat those wires would carry in would destroy the very quantum states they're trying to control. This is what people in the field sometimes call the wiring problem, or the interconnect bottleneck. And for years, it has quietly been one of the biggest threats to the entire future of quantum computing. Not the physics, not the math, the plumbing. Researchers have tried a handful of different approaches to get around this problem over the years. Some have experimented with multiplexing, essentially trying to squeeze more signals down fewer wires. Others have explored optical connections, using light instead of electrical signals to carry information into the cold chamber, hoping to reduce the heat load that ordinary wires bring with them. Some teams have even proposed radically different qubit designs specifically because they might require simpler control schemes. Every one of these approaches has helped chip away at the problem in small increments, but none of them has fundamentally solved it. They've mostly just delayed the moment when the wiring truly becomes unmanageable. What makes HRL's approach different is that it doesn't try to make the external wiring more efficient. It tries to make the external wiring unnecessary in the first place, by moving the intelligence of the system into the cold environment itself. So when a lab announces a breakthrough on qubit counts, it makes headlines. It's flashy. It's easy to understand. Bigger number, better computer, right? But when a lab quietly solves the wiring problem, almost nobody notices. And that is exactly what just happened. The lab in question is called HRL Laboratories, based in Malibu, California. If you've never heard of it, you're not alone, and that's part of what makes this story so interesting. HRL isn't a flashy Silicon Valley startup with a slick marketing team and a 9-figure funding round. It's an old-school American research institution, the kind of place with a long, quiet history of producing breakthroughs that most people never hear about until decades later. This is a lab with deep roots in materials, science, laser research, and semiconductor development, historically tied to major American industrial giants. It has never chased headlines. It has just kept doing the work. In late July of 2026, HRL published a paper in the scientific journal Nature, describing a new kind of quantum processor. On the surface, it doesn't sound like the sexiest headline in the world. A silicon quantum processor that runs itself. But once you understand what that actually means, it becomes clear why this could be one of the more consequential quantum computing announcements of the year, even if almost nobody outside the field is talking about it yet. Here's what HRL actually built. Instead of relying entirely on that external forest of electronics, the racks, the cables, the warm room signal generators, HRL engineers designed a custom control chip that sits inside the cryostat itself, right next to the qubits. Not miles of cabling reaching in from outside, not a separate building's worth of equipment. A single, compact, purpose-built chip, living in the same extreme cold as the quantum processor it controls. This custom chip is built using something called CMOS technology, which is the same basic manufacturing approach used to make the everyday microchips inside your phone, your laptop, and pretty much every piece of modern electronics you own. That detail might sound small, but it's actually one of the most important parts of this story. It means HRL didn't have to invent some exotic new manufacturing process just to make this control chip. They used existing commercial chip foundries, the same kind of factories that already mass-produce processors for the electronics industry. In other words, this isn't some delicate, one-of-a-kind laboratory curiosity that can only be built by hand in a clean room by a handful of specialists. It's something that could, in theory, be manufactured at scale using infrastructure that already exists. Now, here's where it gets genuinely difficult from an engineering standpoint. The environment inside a quantum computer's refrigerator is almost impossibly hostile to normal electronics. We're talking about temperatures around minus 450 degrees Fahrenheit, just a few degrees above absolute zero, the coldest theoretical temperature in the universe. Ordinary electronics don't just slow down at those temperatures. They can behave in completely unpredictable ways, generate unwanted heat, and interfere with the very quantum states they're supposed to be controlling. That's the paradox HRL had to solve. You need active electronics close to the qubits to control them efficiently, but any active electronics near the qubits risk warming up that ultra-cold environment and destroying the fragile quantum states you're trying to protect. Even though this new controller was designed to operate deep inside the cryostat, it's still, relatively speaking, hot compared to the qubits sitting right beside it. Getting a functioning, digitally programmable chip to operate reliably in that kind of environment without wrecking the very system it's meant to support is an extraordinary technical achievement. It's a bit like trying to run a fully functioning engine inside a block of ice without melting the ice. Engineers had to rethink almost everything about how a normal chip behaves at those temperatures. Transistors don't switch the same way near absolute zero. Materials contract and shift in ways that can crack delicate connections. Even the electrical properties of the silicon itself change in ways that standard chip design tools were never built to predict. So this wasn't a matter of simply shrinking an existing chip design and placing it inside the refrigerator. It required years of specialized research into how digital electronics actually behave in that extreme environment, and how to design around those quirks rather than being defeated by them. That's part of why so few labs in the world have even attempted this particular approach. It sits at the intersection of quantum physics, cryogenics, and advanced semiconductor engineering, three fields that don't often overlap, and mastering all three at once is a rare feat. And it worked. According to the published results, this integrated system successfully generated every signal necessary to operate an 18-qubit quantum device, entirely on its own. No real-time input needed from room temperature electronics outside the refrigerator. The chip inside the cold read the qubits, adjusted the signals, and ran a process called error correction, completely autonomously. That phrase, error correction, deserves a moment of attention, because it might be the single most important concept in the entire future of quantum computing. Qubits are notoriously fragile. Unlike the simple ones and zeros inside a classical computer, quantum bits can exist in delicate superpositions, and the smallest disturbance, a stray vibration, a tiny fluctuation in temperature, even background radiation, can cause them to lose their quantum information entirely. Scientists call this decoherence, and it's one of the biggest obstacles standing between today's experimental quantum machines and the kind of large-scale, reliable quantum computers that could actually change the world. Error correction is the process of constantly checking on those fragile qubits, detecting when something has gone wrong, and fixing it, all without directly measuring the quantum information itself, because directly measuring it would destroy it. It's an incredibly delicate dance, requiring constant, high-speed feedback between the qubits and the control system watching over them. Historically, that feedback loop has depended on external electronics sitting outside the refrigerator, receiving signals, processing them, and sending instructions back in, all within fractions of a second. What HRL demonstrated is that this entire feedback loop, this entire error correction process, can happen locally, right next to the qubits, without waiting on instructions from equipment sitting outside in a separate room. That might not sound like a huge leap on paper, but in practice, It fundamentally changes the architecture of how quantum computers can be built. Think of it this way. Imagine trying to run a hospital where every single doctor has to radio a specialist in a different city before making even the smallest decision. It works, technically, but it's slow, cumbersome, and it doesn't scale well if you're trying to treat thousands of patients at once. Now, imagine instead that each hospital wing has its own fully capable medical team, able to make decisions locally, in real time, without waiting on outside approval. That's roughly the shift HRL just demonstrated, in the language of quantum computing. Move the decision-making closer to where it's needed, and suddenly the whole system becomes dramatically easier to scale. This is precisely why so many people in the industry believe the wiring and control problem, not the raw number of qubits, is the true bottleneck standing between today's quantum computers and tomorrow's. You can build a chip with 1,000, 10,000, even 1,000,000 qubits on paper. But if controlling each and every one of those qubits requires a dedicated wire running out to a room temperature rack of electronics, that design simply collapses under its own complexity long before it ever becomes useful. HRL's approach offers a genuine path around that wall. By moving the intelligence of the system inward, closer to where the actual quantum computation is happening. The chief executive of HRL Laboratories, Rob Vasquez, made a comment that's worth sitting with for a moment, because it reframes the entire conversation around quantum computing's future. He pointed out that the technologies which ultimately succeeded in conventional computing weren't necessarily the ones with the absolute highest raw performance. They were the ones that could actually be manufactured cheaply, reliably, and at massive scale. Think about that for a second. There have been countless exotic computing technologies over the decades that were, in theory, more powerful or more elegant than the silicon-based chips that ended up dominating the world. But silicon won, not because it was the flashiest option on a spec sheet, but because it could be mass-produced using standardized, repeatable manufacturing processes. It could be made cheaply, consistently, and in enormous volume. HRL's leadership seems to believe quantum computing is heading toward that exact same fork in the road. And their bet is that the winning approach won't necessarily be whichever lab manages to cram the most qubits onto a single chip in a press release. It will be whichever approach can actually be manufactured using existing industrial infrastructure at a cost that makes sense for real-world businesses and institutions, not just government-funded research labs with unlimited budgets. That's why the use of standard commercial CMOS manufacturing for this new control chip matters so much. It suggests a future where quantum processors aren't handcrafted, one-of-a-kind laboratory instruments assembled piece by teams of specialized physicists. Instead, they could look a lot more like the semiconductor industry we already know, with standardized chips rolling off existing production lines, using proven, scalable manufacturing techniques that the electronics industry has already spent decades perfecting. There's another layer to this story that adds even more weight to the timing. Shortly around the same period this research was published, it was reported that IBM, one of the largest and most established players in the entire quantum computing industry, had signed a definitive agreement to acquire HRL Laboratories. IBM has been one of the most aggressive companies in the world when it comes to quantum computing, investing heavily in both hardware and the broader ecosystem needed to eventually make quantum computers commercially useful. The fact that IBM moved to bring HRL under its own roof right around the time this self-controlling quantum chip technology was published is not a coincidence anyone in the industry is likely to overlook. It suggests that IBM sees exactly what we've been talking about. Not just an interesting academic result, but a genuinely important piece of the puzzle needed to build practical, large-scale quantum computers. When one of the biggest names in an entire industry moves to acquire a relatively quiet, lesser-known lab, immediately after a major technical breakthrough, that's usually a strong signal about where the real value in that breakthrough lies. It also says something about how competitive this space has quietly become behind the scenes. Quantum computing is often talked about as a distant, futuristic technology, something that might matter in 10 or 20 years, but perhaps not right now. Yet the fact that a company as large and resource-rich as IBM is willing to acquire an entire research lab specifically around this kind of control and scaling technology tells a very different story. It suggests that the companies closest to this work don't see it as some far-off curiosity. They see it as a foundational piece of infrastructure, the kind of technology whoever controls it might end up with a meaningful advantage in the years ahead, when quantum computers finally start solving problems that matter outside of a laboratory setting. Acquisitions like this rarely happen on a whim. They happen when a company looks at where an entire industry is heading and decides it doesn't want to be left without a seat at the table. So why isn't this story everywhere right now? Why hasn't it dominated headlines the way announcements about qubit counts or quantum supremacy claims or flashy demonstrations from bigger, more recognizable companies tend to? Part of the answer is simply that this kind of breakthrough is harder to explain in a single sentence. It's not as easy to hype up a headline about integrated cryogenic control electronics as it is to hype up a headline about a new record-breaking number of qubits. Numbers are simple. Bigger numbers feel like obvious progress, even when they don't necessarily reflect real-world usability. Solving the control and wiring problem is a much more nuanced technical story, and it doesn't reduce down to a single dramatic number the way a qubit count does. But if you talk to the engineers and physicists who actually work inside this field, you'll find that many of them see this exact category of problem, the control and scaling challenge, as far more important in the long run than simply piling on more qubits. A quantum computer with 1,000 poorly controlled, unstable qubits isn't necessarily more useful than a quantum computer with 100 perfectly controlled, reliably corrected qubits. In fact, it might be considerably less useful because all that added complexity without a scalable way to manage it often just adds noise, cost, and failure points, rather than genuine computational power. This is part of why some experts have started referring to the current era of quantum computing as something of an engineering bottleneck era, rather than purely a physics bottleneck era. The core physics behind qubits, superposition, and entanglement has been understood for decades. What's held the field back from truly practical, world-changing applications has increasingly become the mundane, unglamorous challenge of engineering. How do you wire it all together? How do you keep it stable? How do you manufacture it reliably? And how do you make the whole system actually scale beyond a small handful of research-grade devices sitting in a university basement? HRL's demonstration is a direct shot at solving exactly that engineering bottleneck by proving that a fully autonomous, self-contained control system can successfully run real error correction on real qubits, using chip manufacturing techniques the electronics industry already knows how to do at massive scale. They've effectively shown a credible path toward quantum computers that could someday be manufactured the way we manufacture ordinary processors today, rather than built like one-off scientific instruments in a handful of specialized labs around the world. Of course, it's important to stay grounded here. This is still an early-stage demonstration. 18 qubits is a meaningful proof of concept, but it's a long way from the thousands or millions of qubits that would be required for many of the most talked about applications of quantum computing, like breaking modern encryption standards or simulating complex molecules for pharmaceutical research. Scaling any new technology from a laboratory demonstration to a fully commercial, mass-manufactured product is never simple, and there will likely be plenty of additional engineering hurdles between this result and a truly large-scale, self-controlling quantum computer sitting in a data center somewhere. There's also the question of cost, which rarely gets enough attention in conversations about cutting-edge technology. Even if this approach proves it can scale technically, it still has to prove it can scale economically. Building specialized cryogenic control chips, testing them at extreme temperatures, and integrating them reliably into a working quantum system is not cheap, at least not yet. The real promise of using standard commercial chip foundries is that, over time, costs should come down the same way they have for every other kind of semiconductor technology throughout history. But getting from a successful research demonstration to an affordable, mass-produced product is often the hardest and slowest part of any technological journey, and quantum computing is unlikely to be an exception to that pattern. But that's exactly why this story matters, even in its early form. Every major technological revolution in computing history has had a moment like this, a quiet, unglamorous breakthrough that didn't grab headlines the way flashier announcements did, but that fundamentally changed the trajectory of what came next. The invention of the integrated circuit itself wasn't originally treated like a headline-grabbing miracle. It was treated, at the time, as a clever engineering solution to a practical manufacturing problem. Decades later, it turned out to be one of the most important inventions in human history, precisely because it solved the unglamorous problem of how to build complex electronics reliably and at scale. There's a very real chance that what HRL just demonstrated could end up looking similar in hindsight. Not the flashiest headline of 2026, not the announcement that made mainstream news outlets scramble to cover it, but quietly, methodically, a solution to one of the most stubborn practical obstacles standing between today's experimental quantum machines and tomorrow's genuinely useful ones. It's also worth pointing out just how symbolic it feels that this breakthrough came from a lab most people have never heard of, rather than one of the giant, headline-dominating tech companies constantly competing for attention in the quantum computing race. In an industry where enormous corporations regularly compete to make the biggest, boldest, most attention-grabbing announcements, sometimes it's the quieter labs, working steadily away from the spotlight, that end up solving the problems that actually matter most in the long run. So what happens next? With IBM's acquisition of HRL now in motion, it's reasonable to expect this self-controlling chip architecture to become a meaningful part of IBM's broader quantum computing roadmap moving forward. If IBM can successfully integrate this kind of localized autonomous control system into its larger quantum computing efforts, it could represent a genuine step forward, not just for IBM specifically, but for the entire industry's approach to scaling quantum hardware. Other major players in the field, who are all wrestling with some version of this exact same wiring and control bottleneck, will almost certainly be watching closely to see how this technology develops from here. Some may try to license similar approaches. Others may accelerate their own internal research into integrated cryogenic control, hoping to avoid falling behind on what could quietly become one of the defining engineering advantages of the next decade. In an industry where the underlying physics is often shared knowledge across competing labs, the ability to actually engineer and manufacture a working system at scale can be the difference between a technology that stays trapped in research papers and one that eventually reaches the real world. It's worth remembering, too, that breakthroughs like this rarely arrive as a single, isolated moment. They tend to build on years of quieter, incremental work that never made headlines at all. The team behind this result didn't wake up one morning and stumble onto a self-controlling quantum chip. They spent years refining cryogenic electronics, testing different chip designs, failing, adjusting, and testing again, long before anything was ready to be published in a journal like Nature. That's the part of scientific progress that almost never makes it into a headline, the long, patient grind that happens in the years before a single dramatic result finally gets announced to the world. It's not exciting to read about in a news article, but it's very often where the real work of innovation actually happens. There's also a broader lesson buried inside this story, one that goes beyond quantum computing itself. It's a reminder that real technological progress doesn't always look like the biggest, boldest headline of the day. Sometimes the most important breakthroughs are the quiet ones, the unglamorous ones, the ones that solve a boring-sounding engineering problem instead of chasing a flashy new record. Somewhere in Malibu, a small team of engineers spent years working on the unglamorous plumbing of quantum computing, the wiring, the control systems, the cryogenic electronics that nobody puts on a magazine cover, and they may have just quietly cleared one of the biggest obstacles standing in the way of practical, real-world quantum computers. While the rest of the world keeps watching the qubit count race, chasing bigger numbers and flashier headlines, it's worth remembering that the real breakthroughs sometimes happen far away from the spotlight, in a quiet lab, solving a problem nobody else was paying attention to. And if history is any guide, those are often exactly the breakthroughs that end up changing everything. So the next time a headline promises a bigger qubit count or a flashier record, it might be worth asking a quieter question instead. Not how many qubits does it have, but can anyone actually build it, run it, and trust it at scale? That question, far more than any single number, may end up deciding who actually wins the race.